Welcome to part 3 of this virtual series, Decoding AI and Hydrology for Water Management Decisions. I'm one of your co-hosts, Eliza Hale, and I will be presenting this third part with my co-host, Laura Reed. In this part of our virtual series, we'll be going over a brief history of how machine learning has been used in hydrology. We'll be talking about how the science has evolved and how we've gotten to where we are today. Over to you, Laura.
Great, thanks, Eliza. All right, so we've reviewed neural networks and LSTMs as a particular branch of machine learning models. And if we trace back the first application of machine learning models for hydrology, we can go to 1995. Where there's a paper, which we can link to the comments in this episode. And interestingly, it wasn't until about 20 years later that folks actually took this concept and did some larger benchmarking experiments to understand how well LSTM models do at predicting streamflow compared with some of the more typical conceptual models that are used by industry and government in the United States and North America. So the plot here on the left is something called the CAMELS data set. It's just showing a bunch of different dots which represent basins at which the LSTM and conceptual models were all compared. And this was a big effort. So there's 531 basins that this paper, it's Kratzert et al. 2019. Again, we'll link that. And we were actually co-authors. Our CTO is a co-author on this paper. And essentially what this paper showed was it took all the streamflow predictions for a validation period compared with a bunch of different models. And some of these models, they had different parameter settings. And so there's a couple different lines from each one. But the take home is that if we look at the Nash-Sutcliffe efficiency, which is a performance metric, the more accurate models have the lines closer to 1 or on the right side of the plot. And so comparing some common conceptual hydrologic models against the RFC, which is the River Forecast Center, kind of state-of-the-art government forecast here in the US, against LSTMs. LSTMs in general outperformed the other conceptual models that are used. And so this was a big eye-opener for folks to start paying attention and understanding how these models worked. Fast forward to not even a year later, again, the same core group, Kratzert et al., 2019, a second paper, took an LSTM that was untuned. So a model that didn't have information about the gauges, we can call it an ungauged prediction, and compared that with these government models. So the SAC SMA is one that we talked about earlier. It's the model that NOAA generally uses. The NWM is the national water model, and then a couple different versions of an LSTM. And what this plot shows, again, it's the same on the left there, the same kind of like cumulative performance across the 531 basins, is that even a ungauged LSTM outperforms a calibrated version of the NOAA's models. And then the next paper, so then after that, more folks are starting to use these and understand them. There was another paper that came out last year by Julie who is out of Canada, where they did a huge, really nice, rigorous study of different models in the Great Lakes region. And you don't need to really pay attention to all the colors and all the lines and rows there. But in this experiment, they took a bunch of different kinds of models, really common ones, VIC, Raven, and then there's an LSTM, a lumped version of the LSTM. And that essentially outperformed the other models that were tested across most of the sites and across the full validation and calibration period. So these models are useful. They're not all right, as we've talked about, but there's something there that we can learn as scientists and can be helpful for water management decisions. So from those literature papers, we were co-authors on some of those papers and are involved with academic partners. Essentially, that LSTM, that version that was tested is what we started with HydroForecast, and we've only built from there. And so the next section of this, we'll kind of talk about HydroForecast and actually show an example in our dashboard. So Hydro Forecast is the upstream text product for Streamflow forecasts. And this is an operational forecasting service where we pull in different weather forecasts, satellite inputs, land surface inputs, just like a typical physical model would, as we talked about before. And we put that into our LSTM. We have a big data pipeline that does this all automatically, and we serve out hydrological forecasts to our customers and partners. The short-term model, this is sort of the workflow of that model where we take our inputs, and we've listed some of them here. Our model is unique in that we pull in multiple weather forecasts and also remote sensing data from snow and vegetation. And then we put that through our neural network, which now everybody understands completely. And we get a probabilistic forecast out of that. And I'm showing here the 10-day forecast, but we also do a seasonal forecast as well. And to kind of bring this into perspective for what the everyday user looks at, here's an example of a demo site in California where we have our forecast set up. This is our dashboard. So for our users that like to come on and see what the forecasts look like, this is Folsom Lake, Folsom Reservoir. This is Lake Tahoe. So Central California here. So this is our basin that we have set up, and we run operational forecasts here for inflows into Folsom Lake. And if I scroll down here, so you'll notice a couple things. We have the basin split into little sub-basins, and we actually have a distributed version of our neural network model that makes predictions on each of these sub-basins, routes the flows downstream, and uses gauges where available, for example, right here, to assimilate flows into the points of interest. So what we show our customers is that probabilistic 10-day forecast, which is hourly and updates every 2 hours, along with the weather. So the inputs that we're using are all available. These are all something that our customers can access, and they help tell the story of why the forecast is doing what it's doing. Oftentimes it's the weather, whether it's temperatures changing during melt time, lots of precipitation, lots of disagreement in the precipitation. And so this is a way for our customers to kind of see into that black box, if you will, and interpret the forecasts themselves. The model takes information about snow. So we are pulling information from SNODAS and also from the VIIRS satellite from NASA. And so we can see how snow cover and snow water equivalent have evolved over the last year. And that can help folks kind of understand how much storage is still there in terms of snow that will come through in the season. Great. And at the end of the day, I think there's still a question of, how well does this LSTM model do in operations? And we were fortunate enough to be a part of a year-long co-sponsored competition that was hosted by the Bureau of Reclamation and a hydropower interest group, where we were an entrant along with a lot of other groups that make forecasts, including NOAA and some other entities. And our forecasts, they had 5 different categories. They had 5 different regions. And across those different 25 options, our forecast did quite well. These metrics are calculated by RTI, a third party. And so this model is not only good in an academic setting, but also in a live operational setting. We're seeing a lot of accuracy compared with the other options out there. Eliza, over to you to wrap us up.
All right. Thank you so much. We are so happy to bring this virtual series to you. We have been excited about machine learning and its applications to hydrological science for a long time, and it's fun for us to get to share it with everyone. We hope that you'll take away a little bit more of an understanding of the basics of artificial intelligence and machine learning terminology, as well as an appreciation for the value that ML can bring to hydrological science. Thanks again for joining us, and check out our show notes for additional resources.